There is a very seductive assumption in modern AI research. If you can solve a task with a short, deterministic program, you should be able to teach that procedure to a language model as a chain of thought. Just write out the program steps in natural language, fine-tune a smaller model on those rationales, and it will reproduce the reasoning. This intuition powers everything from rationale distillation to reinforcement learning from verifiable rewards. But what if that intuition is fundamentally wrong for an entire class of procedures? What if a verifiable search simply cannot be distilled into a chain of thought? I ran a controlled study to test exactly that. I built a benchmark of 9 reasoning tasks, each generated by a deterministic program. The setup is deliberately clean. The training and test data come from the same generators, so a held-out slice of training accuracy predicts test performance directly. I reverse-engineered each generator into a Python solver, rendered their internal steps as synthetic chain-of-thought traces, and distilled them into a rank 32 LoRA adapter over a 30 billion parameter hybrid Mamba 2 and mixture of experts model. 5 of the 9 tasks transferred flawlessly. 4 lookup and arithmetic tasks hit near-perfect accuracy. But one task, a cryptarithm solver, completely collapsed. Despite a backtracking search solver answering 71% of the instances, the fine-tuned model never broke 5% accuracy. Not after 11 different chain-of-thought designs. Not after reinforcement learning from verifiable rewards. Not after self-training on its own correct rollouts. So what broke? The model wasn't missing arithmetic capability. It executed the column math correctly 97 to 100% of the time. It could even recognize the correct cipher mapping in its top 8 candidates 71% of the time. The failure was strictly in carrying the search forward as a left-to-right derivation. I call this the verdict as token phenomenon. Under teacher forcing, the model is trained by feeding it the correct next token at every step. This means the verdict always appears in a context where it happened to be correct. The model learns the phrase, not the function. At inference, when it generates tokens freely, those verdicts fire blindly, completely unmoored from the numbers they were supposed to be derived from. It's a textbook exposure bias failure, localized to the single most load-bearing token in the procedure. Is this just a limitation of small models or a specific architecture? I ran a controlled intervention to prove causality. I took the exact same cryptarithm instances and revealed a fraction of the digit-to-symbol cipher key in the prompt. That instantly turned the hidden search into a forward lookup. Revealing half the key barely moved accuracy, but revealing the full key lifted performance from 3% to 57%. That is a 15-fold jump on an otherwise identical task. Forward derivability is the causal lever. And to rule out architecture bias, I fine-tuned the identical corpus on dense transformers, MoE transformers, and even sampled frontier models up to 671 billion parameters in context. Every single backbone hit the exact same floor. The search distillation ceiling is architecture general. The binding constraint is task intrinsic. When a procedure's only solution is backtracking search over information-free structure, no faithful forward chain of thought exists to imitate. Does this mean the task is unlearnable? No. It just means you cannot distill the search itself. The competition's first-place solution reached 92% accuracy by doing the exact opposite. They didn't teach the model to search. They precomputed the combinatorial core offline into a finite catalog of 4,205 candidate entries per signature. The model memorizes that catalog through heavy fine-tuning. At inference, it simply recalls the candidate list and runs a bounded in-trace verification. The search is removed from the trace entirely. What transfers is memorization and bounded verification, not search. The lesson here is sharp and mechanistic. Solver coverage is a necessary but badly insufficient condition for learnability. It tells you the answer exists, but it doesn't tell you whether your model can reason its way to it. A verifiable search is not a learnable chain of thought. The dividing line is forward derivability. For tasks that require carrying explicit search state, constraint propagation, and backtracking over unbounded structures, supervised fine-tuning will only ever learn an unfaithful surface form. If you want to bridge the gap, you either have to teach the model a search it can actually execute at inference, or you have to restructure the problem so the combinatorial explosion happens offline, leaving only recall and verification in the trace. Distillation has hard limits, and understanding exactly where those limits bind is the only way to push past them.